So in this lesson, we're going to be defining a really, really important property that's actually going to carry through the rest of our understanding of statistics. And it is a random variable. It's a random variable. Okay. And so to introduce this idea of a random variable, we're going to imagine a hypothetical experiment, a hypothetical random experiment where we've thrown 2 dice. And so we can just write down the outcome space of this experiment. It's the set containing the pairs 1 and then a 1, or I could get a 1 and then a 2. I could get, and so on until you get a 1 and a 6, and then I can get a 2 and a 1, a 2 and a 2, a 2 and a 6. And these sort of combinations of possible dice rolls will continue. They'll continue until I get a 6 and a 6. And so there are 6 possible faces on a die, and there are 2 die, and so there are 36 possible combinations of dice rolls that we have here. 36 possible combinations of dice rolls. Okay, so what we might want to know is not every single nitty-gritty detail. We don't want 36 different combinations. What we might want to know is something called x, and we'll call x the sum of the die face values. Okay, and so for example, what I mean here, if I got a 1 and then a 6, x would be equal to 1 plus 6, it'd be equal to 7. Okay, and so this is sort of just a transformation of our data, just to sort of make things simpler, just because we wanted less detail in our outcomes. And if we want to be more formal about this, we can actually make x a function that takes our outcomes, like 2 and 6, and puts them into the sum of those outcomes. So x is a function that takes as input, outcomes, omega, and gives us an output, real numbers. Okay, so in this case, it's taken the input 2, 6, and it's given the output 8, but it could also take the input 6, 6, and give us an output 12. Okay. And will we also know that since all these 36 outcomes are equally likely, we also happen to know that the probability of getting this particular outcome 2, 6 is equal to, well, one possible outcome out of 36 equally likely outcomes. It's 1 in 36. Okay. But then a natural question that we're going to ask is, what is the probability that this sum of the die face values is equal to 8? Okay? So if I go over all my possible outcomes, what is the probability that that sum is equal to 8? So that's going to be our next question. So clearly we can sort of intuitively see that the probability of this is going to be equal to the probability, just like any other probability, the probability of some event. And so we're going to define that event A as just the set of all outcomes that x, so the set of all outcomes such that this rule is satisfied, such that x of the outcome is equal to 8. And so we're going to collect together all the different experimental outcomes such that the sum of the die face values is equal to 8. We're going to collect them together in an event. We're going to ask what is the probability of that event. So what we're going to do is manually figure out which outcomes sum to 8. And so we've got 2, 6. Okay. We've got 3, 5. And we've got 4, 4. And for each of these two, we've got the opposite. We've got 6, 2. A 6 and then a 2, and we've got a 5 and then a 3. And so there's 5 possible equally likely outcomes out of the 36 possible outcomes that the face values on the die sum to 8. And so we can write the probability that x equals 8 equals 5 on 36. And so this is a very common thing that we'll want to do. We'll want to transform the data in some way. We'll say, okay, I want to take the sum of the die's face values, but then I also want to know what the probability of getting a particular value for that, that sum of the face values is. And to understand this in a general sense, what I'm going to do is just walk you through this problem in a really general setting. And so what we're going to do is we're going to consider sort of 3 different places we can be. And first of all, we can be in the outcome space, okay? And second of all, we can be on this little number line from 0 to 1, okay? And third of all, we can just be in the real numbers. Okay, so just any number we want. So for example, what we had before, like 8 being the sum of the face values on the die. And we've already introduced in the last tutorial this idea of a probability. And a probability takes events in the outcome space and it maps them to these numbers between 0 and 1. So we can say, okay, this P thing, this P function takes me from outcomes, or events, takes me from events, like A, takes me from events in the outcome space to probabilities. And so we can go to here, the probability of A. Okay. And similarly, we can define random variables, replace the text up here, random variables as functions that map from the outcome space to the real numbers. And so where I had this probability here I've got a possible, one of many possible random variables that map from the outcome space to the real numbers. And the example that we just had with the sum of the face values on the die mapped us from an outcome, for example, 2, 6. So the face values being a 2 and a 6. It mapped us from that to the real number 8, where 8 was the sum of things on the die. And so we can think about random variables map from events to numbers. Okay. And so they'll take us from events to numbers, or from outcomes to numbers. And we've got probabilities. They map from events to probabilities. And the way that we sort of define, the way that we sort of get for free, we get this idea of the probability of a random variable being equal to a particular number. So for example, here I might have 8, a particular number. The way we get that is we say, okay, well, what is the set of all outcomes, the event that maps to this particular real number? And then we ask ourselves as well, what's the probability of that event? And so we get this connection, even though the random variable maps from outcomes to real numbers and has nothing to do with probability technically, we can define the probability of our random variable being equal to a particular number as just the probability of all the different outcomes that this random variable maps to that particular real number. And so just quickly put that in our set notation, we can say the probability that a random variable x takes on a particular value, so we'll represent particular value by a little x, which is just equal to the probability of some set A, some event A, where A is going to be equal to the event that contains all the omegas, such that this random variable, this function, maps that particular outcome to this particular value, little x. Okay. And so we have 2 ways really that we can think about random variables. At a really fundamental level, random variables are just functions which take as input different outcomes or events and give as output simply real numbers. Or we can use this relationship here between probabilities and events and the output of our random variables, and we can also think of random variables as sort of relationships between real numbers and probabilities, which is what this equation down here encapsulates. We've got a relationship between real numbers, like little x, and probabilities here and here.